We love the idea of a cheat code. Pop culture has spent decades selling us a specific fantasy that inside our skulls sits a massive, dormant reserve of computing power. If we can just find the right trick, those dark pathways will erupt into life, granting us instant, effortless mastery. This desire birthed the famous 10% rule, the claim that we leave 90% of our brain power entirely unused. The origin traces back to the 1890s, when American psychologist William James theorized that humans use only a small part of our mental resources. Over time, that vague observation was codified into a strict mathematical percentage, falsely bolstered by fabricated quotes attributed to Albert Einstein. By the 1990s, the Mozart effect offered a new shortcut. The public was told that playing classical music CDs to infants, or even unborn babies, would hack their developing brains and boost their intelligence. This search for a quick fix extended to how we handle complex mental health disorders. For years, conditions like severe depression were reduced to a chemical imbalance, a mechanical shortage of serotonin that a single daily pill was expected to resolve. We cling to these myths because our biology seeks the path of least resistance. We want a magic lever to pull because acknowledging the demanding physical reality of our biology requires actual work. Look at this chart representing the data from a 2022 umbrella review led by Professor Joanna Moncrief. By aggregating decades of research, her team demonstrated there is no compelling evidence linking depression to a serotonin deficit. The chemical imbalance evidence essentially evaporated. The Mozart effect met a similar fate. The foundational 1993 study by Francis Rauscher tested 36 university students on a specific spatial reasoning task involving cutting and folding paper, not general intelligence. When other researchers tried to replicate the results, they failed. Classical music does not make children smarter. As for the 10% rule, it fails on basic thermodynamics. The human brain accounts for roughly 2% of our total body weight, yet it devours 20% of our daily calories. Evolution would not select for an organ this expensive if it were mostly dormant. Inside that tissue, individual neurons are firing hundreds of times per second. Even when we are deep in sleep, the structure remains active, burning through metabolic fuel to consolidate memories and perform maintenance. If all our cultural shortcuts are scientific fictions, where does that leave us? Are our cognitive limits strictly capped, or have we simply misunderstood the biological mechanics of how we actually improve? Our true capacity for growth is found in neuroplasticity. Every time we learn a name, memorize a fact, or practice a skill, our brain is physically growing new connections between neurons. It is a time-intensive physical rewiring process that requires repetition and effort. Recognizing this growth requires us to abandon older scientific models. In the mid-20th century, scientists often viewed the brain as a rigid machine with isolated, compartmentalized functions. This view was heavily influenced by the work of Roger Sperry in the 1960s. Sperry studied patients who had their corpus callosum, the thick band of nerve fibers connecting the two halves of the brain, severed to treat severe epilepsy. He discovered that when you separate the hemispheres, they act independently. The left hemisphere analyzed and articulated language, while the right hemisphere recognized shapes and objects, but could not speak. Sperry's work earned him the Nobel Prize in 1981. It provided the first clear evidence of how different regions specialize in specific tasks, but it also triggered a pervasive misunderstanding in the general public. Pop culture turned his clinical observations into a personality test. We started categorizing people as analytical left-brained thinkers or creative right-brained artists, treating the skull like it contained two competing roommates. While brain regions do specialize, cognitive power is never found in isolation. Solving a complex math problem or painting a portrait requires regions across both hemispheres to rapidly communicate and coordinate. Look at these fMRI scans. Modern neuroscience identifies the brain as a holistic, vibrating web governed by three primary networks. First is the default mode network, or DMN. This network dominates when we are at rest. It powers our internal thoughts, our daydreaming, and our self-reflection. Second is the central executive network, or CEN. This system engages when we need high-level focus. It takes over for complex problem-solving, decision-making, and managing heavy cognitive loads. Third is the salience network.
This is the brain's switchboard operator. It constantly monitors our environment for important stimuli and toggles our brain state between the inward-looking DMN and the outward-focused CEN. We can apply this network logic to the Mozart myth. When you try to study while listening to complex music, especially if it has lyrics, your brain automatically processes that audio for meaning. This overloads your working memory and disrupts the central executive network you need to learn the material.
Silence or steady white noise is more effective. Intelligence and focus are not about activating a dormant percentage of gray matter. They rely on the seamless, harmonious switching between these three networks, matching the right cognitive tool to the right task. This network model changes how we approach mental health. Chronic, treatment-resistant depression is increasingly understood as a mechanical network malfunction. If the salience network becomes impaired, it fails to execute the switch between internal and external focus. A person can become trapped in the negative rumination loops of the default mode network, unable to transition to goal-directed tasks. This is why interventions like transcranial magnetic stimulation, or TMS, are gaining traction. Instead of flooding the system with chemicals, TMS uses magnetic fields to physically stimulate specific regions, like the dorsolateral prefrontal cortex, forcing the networks to rebalance and restore their ability to switch states. The biological reality is that our brain is a highly adaptable, incredibly demanding ecosystem. There is no magical on switch waiting to be flipped, and no hidden reserve of inactive tissue. To reach our actual potential, we have to abandon the fiction of the easy shortcut. Progress requires the demanding reality of focused practice, managed cognitive load, and network harmony.